Before we move into the next unit, let's take some time to review synthetic division so that we can then use it for some more complex operations. Recall that in order to do synthetic division, we have to be dividing by a binomial that is linear with a leading coefficient of 1. Also, remember it's in the form of x plus, or x minus k, x minus k. So we're looking for a binomial in this form in order to do synthetic division. And we set it up by using the box and stripping out all the coefficients, or all the variables, and leaving just the coefficients of the polynomial that we are dividing. So here we're dropping the x to the third, the x squared, and the x, and we're just leaving the 4, -3, 6, and 5. And inside the box will be the value of k. If x minus 1 is our expression x minus k, then k equals 1. And so that's the number that we're going to put in the box. And then we're going to repeat the process of addition and then multiplication until we get to the quotient at the end. So we'll start by bringing down the 4, multiplying 1 by 4 to give us 4, and that goes up into the next box. And then we repeat the addition and multiplication. We add -3 to 4 is 1, multiply by 1 goes up here. 6 plus 1 is 7. Multiply 7 by 1 to get 7, and then we add 5 and 7 to get 12. And this is our quotient down at the bottom. And so now we can rewrite our quotient. Our leading term will be 1 degree less than what we started with. So since this was x to the third, this will be x squared. And then we have plus x, plus 7, and then we have our remainder here. So we'll write our quotient as 4x squared plus x plus 7 plus the remainder over the divisor. Let's go ahead and repeat the process. So since we're dividing by x plus 2, our value for k is going to be -2, so that goes in the box. And then we're going to go ahead and put all of our coefficients. But notice we're missing our x term. So we need to include a placeholder 0 in where this x term would be so that we have all the parts of our dividend. So the coefficients are 1, -2, -11, here's our placeholder 0, and 34. Again, just as a reminder, this represents our 4th degree, 3rd, 2nd, 1st, and our constant term. We need to be able to count all the way down to 0 to make sure that we have all of our coefficients. So now we can go through the process of adding, and then multiplying, and then adding, and then multiplying, and then adding, and then multiplying, adding, and then multiplying, and then adding. And so here's our quotient. Again, we're going to go 1 degree less, and since we started with a 4th degree, this is going to be x to the third, x squared, x constant, and the remainder. So we'll write our quotient as x to the third minus 4x squared minus 3x plus 6 plus 22 over x plus 2. I encourage you to try this one on your own. Go ahead and pause, and then check your work with me when you're done. We're going to set -3 in the box, and we're going to check our coefficients. I've got 4, 3, 2. I'm missing the linear term again, so I need to include a placeholder 0. So we'll have 1, 3, -5, 0, and 12. Bring down and multiply, add, multiply, add, multiply, add, multiply, and then add. We're going to go down by 1 degree, so since we started with 4th, this is 3rd, this is squared, linear, constant, remainder. So we'll write our quotient as x to the third minus 5x plus 15 plus -33 over x plus 3. So now we're going to review the remainder theorem. And we talked about this briefly in a previous unit when we were doing polynomial division. If we're dividing a polynomial by x minus k, meaning that we can use synthetic division, then the remainder is equal to evaluating the function f of k. In addition to that, when we divide f of x by x minus k and the remainder is 0, It means that x minus k is a factor of that polynomial, and k is a 0 of f of x. So this is going to be very important for our next unit, is identifying if and when the remainder of the synthetic division is 0. And this is how we will factor our higher degree polynomials. So first thing we're going to do is we use the remainder theorem to evaluate the function. So we're going to evaluate f of negative 2. And we're able to use synthetic division because it's asking for us to use the remainder theorem. Here they're giving us the value of k. K equals negative 2. K goes in the box. So our coefficients, we have third, second, first, and constant. So we don't need any placeholders. So we can put our coefficients in and perform the synthetic division. So we'll go through the process. We're going to add, we're going to multiply, we're going to add, we're going to multiply, we're going to add, we're going to multiply, and then we're going to add, and we get to the end. Our remainder is 19. Remember, we're using the remainder theorem. So, since the remainder is 19, that means f of negative 2 equals negative 19. Why don't you try this next one on your own? Go ahead and pause and then check your work with me when you're done. So we're evaluating f of k, and they told us that k is 4. So 4 is going to go in the box. Note we're missing the linear term, so we need the placeholder 0. So our coefficients are negative 1, 8, 0, and 63. We'll go ahead and start the process of adding, multiplying, adding, multiplying, adding, multiplying, adding. Again, we're using the remainder theorem. Our remainder is 127. That means that f of 4 equals 127. Now we're going to extend it to the second part, that if the remainder is 0, we're identifying a factor and a 0 of that polynomial. So we're going to determine whether or not this value is a 0 of the polynomial. We'll also talk about whether or not it's a factor, because if the answer to the first question is yes, the second question is also yes. So they're giving us the value of k, so we'll go ahead and set that in our box, and then we need our coefficients. I've got 4, 3, 2, 1, 0, so I don't need any placeholder zeros. So my coefficients are 2, 12, 6, negative 5, and 75. So we'll go ahead and we'll start the process. We'll add, we'll multiply, we'll add, we'll multiply, we'll add, we'll multiply, we'll add, we'll multiply, we'll add, and we get a remainder of 0. So, yes, negative 5 is a 0 because f of negative 5 equals 0. And we use the remainder theorem to evaluate f of negative 5. Now, conversely, this also means that if x equals negative 5 is a 0, if I were to set this equal to 0 and kind of undo our 0 factor property, that means that x plus 5 is a factor. And what we've done is we've actually factored this polynomial. So I took this fourth degree polynomial, I factored out x plus 5, and I'm left with the quotient of 2x to the third plus 2x squared minus 4x plus 15. I've now taken a fourth degree polynomial, factored out a binomial, and was left with a third degree polynomial. And theoretically, we could continue this process, and that's something that we're going to be doing in future lessons, is we're going to continue this process in order to completely factor polynomials. Let's check to see if this one's a 0. So they give us the value of k. We've got our fourth degree, but we're missing the third degree, so we need a 0 placeholder. 1, negative 3, and then 1. So we'll add, we'll multiply, we'll add, we'll multiply, we'll add, we'll multiply, we'll add, we'll multiply, we'll add. And we see our remainder is not 0. So no, negative 4 is not a 0. because f of negative 4 does not equal 0. Now here we have a 0 that's actually a non-real complex number. We can still do the same process, even though it's going to be a little bit messier. You may want to use your calculator to kind of help you, but I'll work it out the long way. If your calculator is in the non-real complex mode, the A plus BI mode on the TI-84, you can do these calculations in your calculator. Just make sure you're paying attention to the need for any parentheses or anything like that. So make sure you're paying really close attention to that. But we're going to work it all out by hand. So we're going to need a little bit of space off to the side, but we'll go ahead and set up our value for k. And I want to see if 1 plus 2i is a 0 to this polynomial. So we have our coefficients 1, negative 2, 4, 2, and negative 5. And actually, I'm going to give myself a little bit more space because I'm dealing with complex numbers. So I want a little bit more room to do these operations. So I'm going to space those out a little bit more. The process is going to be the same. Just the arithmetic is going to differ a little bit. We still bring down the 1, and now we're going to multiply 1 by 1 plus 2i. Well, that's just going to be 1 plus 2i. Now recall, when we're adding real and complex numbers together, we add the real parts, and then we add the non-real parts. Negative 2, you can imagine as being negative 2 plus 0i. So we're going to have negative 1 plus 2i. Now we're going to multiply negative 1 plus 2i by 1 plus 2i. We're going to multiply these two together. So 1 plus 2i times negative 1 plus 2i. We're going to use our distributive property. So we'll have negative 1 plus 2i minus 2i plus 4i squared. Well, the 2i and the negative 2i are going to cancel out. I squared equals negative 1, so we have 4 times negative 1, so that gives us 1 minus 4, giving us a value of negative 5. So negative 5 goes up here. Then we're going to add 4 and negative 5. We go back to the blue, and we're going to get negative 1. We're going to multiply negative 1 by 1 plus 2i. That gives us negative 1 minus 2i. Again, we can imagine this is 2 plus 0i, leaving us with 1 minus 2i. Now we're going to go ahead and multiply 1 plus 2i by 1 minus 2i. And we'll use our distributive property again. We get 1, negative 2i, positive 2i, negative 4i squared. The negative 2i and the positive 2i, those will cancel. And then the I squared becomes negative 1, so we're left with 1 plus 5. Sorry, getting ahead of myself, 1 plus 4, which then gives us 5. So the 5 goes up here, and then we go ahead and we add, and we get 0. So we see that our remainder is 0. That means that, yes, 1 plus 2i is a 0 because f of 1 plus 2i equals 0. When we did the synthetic division, we got a remainder of 0. Now, side note, we can talk about the factors. We factored this polynomial. We just ended up with a polynomial that has non-real coefficients. And so since we had a 4th degree polynomial, this quotient is technically x to the 3rd plus negative 1 plus 2i x squared minus x plus 1 minus 2i as the constant term. So that would be that polynomial. And then we factored out x minus 1 minus 2i because that would then give us the 0 of 1 plus 2i. We'll go into much more detail about these complex factors and how we write them in a future section, but I just wanted to give you a little bit of preview of what that looks like. Right now we're focusing on whether or not it is a 0, and because the remainder is 0, that means that the value of k is a 0 of the polynomial. And recall from previous units that a 0 of a polynomial is the x-intercept of that polynomial. So here we have a non-real x-intercept, which means it doesn't actually intersect the x-axis, but in terms of our real numbers, we've found an x-intercept of negative 5 for this function, which is why f of negative 5 equals 0. When x is 0, when x is negative 5, the y value is 0.